Assalamu alaikum. I am MD Muzad Al Tarif, ID beyond 80305039. Course Design and Analysis of Algorithm. Course code 2210. Algorithm name HipSort. Included topic. Definition of HipSort. HipSort in graph. Main theme of HipSort algorithm. Working principle of HipSort algorithm. How work HipSort. Algorithm of HipSort. Implementation in Java. Time complexity of HipSort. Now definition. A heap is a special tree-based data structure in which the tree is a complete binary tree. The heap is used in an elegant sorting algorithm called heap sort. Generally, heaps can be of two types: max heap and min heap. Max heap. In a max heap, the key present at the root node must be greatest among the keys present at all of its children. The same property must be recursively true for all subtrees in that binary tree. Graphical representation. We can see a binary tree. Here 100 is a root of 40 and 50. We know 100 is obviously greater than 40 and 50. Now 40 is a parent of 10 and 15, and 40 is greater than 10 and 50. 50 is a parent of 45 and 40. 50 is greater than 45 and 40. So we see that every parent is greater than his child. So this tree is called max heap. Min heap. In a min heap, the key present at the root node must be minimum among the keys present at all of its children. The same property must be recursively true for all subtrees in that binary tree. Graphical representation. Here, 10 is the parent of 15 and 13, and 10 is smaller than 50 and 13. 15 is a parent of 40 and 45. So 40 and 45 is greater than 15. 30 is a parent of 45 and 35. 30 is smaller than 45 and 35. So it is min heap. Main theme of heap sort algorithm. This algorithm uses the data element of sorting ascending or descending order. The graph is stored as an array. If a node at index I, then its left child is at 2 into I, its right child is at 2 into I plus 1, its parent is at I divided by 2. If the heap is max heap, then its parent is greater than child. If the heap is min heap, then its child is greater than parent. Working principle of heap sort algorithm. Max heap insertion. Here is the array 15, 20, 7, 9 and 30. Firstly insert 15. 15 is the parent of his left and right side. So next element 20, insert its left side. Now we check 15 is greater than 20. No, 15 is not greater than 20. We know every parent is greater than his child in max heap. So swap and see. 20 is parent and is its left child 15. Now check 20 is greater than 15. Yes. And then third element 7 insert in 20's right side. Now check 20 is greater than 7. Yes, 20 is greater than 7. Now fourth element 9 insert 15's left side and check 15 is greater than 9. Yes. And the last element 30 insert in 15's right side and check 15 is greater than 30. No. So swap and see. Now check 20 is greater than 30. No. Again swap and see. Now see every parent is greater than his child and this is the maxi. Mean heap insertion. Mean heap insertion is the reverse process of max heap insertion. Firstly insert 15 and its left child is 10 and check 15 is smaller than 10. No and swap. And third element 20, insert 10's right child and check 10 is smaller than 20. Yes. And 25, insert 15's left child and check 15 is smaller than 25. Yes. And last element 5, insert 15's right child and check 15 is smaller than 5. No. And swap. And now check 10 is smaller than 5. No. And again swap and we can see this is mean heap. How heapsort works. Since the tree satisfies max heap property, then the largest item is stored at the root node. Swap. Remove the root element and put at the end of the array and put the last item of the tree at the vacant place. Remove. Reduce the size of the heap by 1. Heapify. Heapify the root element again so that we have the highest element at root. The process is repeated until all the items of the list are sorted. We can see the first tree. It is a max heap. The root 20 is greater than all elements. Its last element is 9. We know heap sort condition is swap root and last element. So swap 20 and 9. That is next tree. And we can see 20 is set as perfect position of the array. So remove 20 and see the next tree. But this tree is not max heap. So heapify and see next tree. That is max heap. And now swap 10 and on. Now see 10 set as position. So remove 10 and again heapify and swap 9 and 5 and see 9 set has position and remove 9 and heapify again. Now the root element is 6 and last element is 1. So swap 6 and 1 and see 6 is set as position and remove 6 and again heapify. Now see the root element is 5 and last element is 1. So swap 5 and 1 and see 5 is set its position. So remove 5 and see one element in the tree and it set perfect position and see the array is sorted. Algorithm of heap sort. Function heap sort. Firstly, function heap sort. Pass a and count, where a is an unordered array and count is an array of length. And then call a function heapify, where pass a value a and count and set e is equal to int is equal to count minus 1 and check while int greater than or is equal to 0, then swap root and last element and then called function shift down, where pass values a, 0 and in, and last set int is equal to int minus on. Now the happify function set start is equal to count minus 2 divided by 2 and check start greater than or is equal to 0, and then it called shift down function, where pass values a, start and count minus on, and set start is equal to start minus on. And last function shift down, where get attribute a, start and end, and set root is equal to start. Now, while root into 2 plus 1 less than or is equal to end, then set child is equal to root into 2 plus 1 that points left child, and check if child plus 1 less than or is equal to end and left child less than right child, then set child is equal to child plus 1, and check root less than last child, then swap root and last element and set root is equal to child, else return. Implementation of Java. Here three functions. First function heap sort, with sorting unordered array, and second function is heapify, which heapify makes heap, and last function is shift down, and main function were called all function. Sample input and output. Enter element amount 5, enter value 8, 4, 10, 2, 1, and sorted array output sorted array 1, 2, 4, 8, 10. Time complexity of heap sort. Time complexity of heapify is big O log n. Time complexity of create and build heap is big O n, and overall time complexity of heap sort is big O n log n. Thank you.
Red Black Tree by Nahid Ryan. Design Analysis of Algorithm Lab, CSCL 2210. So what is the red black tree? Red black tree is a self-balancing binary tree in which each node contains an extra bit for denoting the color of the node, either red or black. Now, before going much further, we have to know some fundamentals. So what are the fundamentals? Before diving into this topic, let me get this straight. You should know binary search tree and its basic. Only then you will be able to understand what is a red black tree. So if you know binary search tree, so a question may arise, that is, why do we need red black tree? Here is an example. In a binary search tree, we know that it maintains data in natural order, but it does not impose any restriction on the size and length of a tree. A binary tree that is not balanced properly can be similar to a linked list. Here we can see 1, 2, 3, 4, 5, 6. If we create a binary search tree out of this data, then the start node will start with value 1, and the arrangement will look like this: 1, 2, 3, 4, 5, 6. Therefore, the depth of the tree will be 5. So you have to, so if you search a value of 5, you have to go to depth of 5. But in a red black tree, since it is balanced, so it will, the tree will look like this: 1 2 3 4 5 6. Here 4 is the parent node, uh, root node, and 1 is the leaf, and 6 is the leaf. As a result, the depth of this tree is 3. So from this, we can conclude that a red black tree is an advanced binary search tree. Now, what will be the time complexity? The time complexity will be log n in everything: searching, insertion, deletion. The only most important thing is that the in red black tree during insertion, it does extra operations in order to balance the tree. So there are some properties of red black tree. What are the properties? So there are 4 properties. Sorry, 5 properties. So the properties are red or black property, root property, leaf property, red property, and depth property. Now, what is red/black property? Here it states that every node is colored either red or black. In root property, the root is black, which means that the root will always be black. In the leaf property states that every leaf that is nil is black. And what is red property states, if a red node has children, then the children are always black. What does the depth property says? For each node, any simple path from this node to any its indecent leaf has the same black depth, the number of black nodes. Now, this may be confusing to some of you, but later on the slides, I'll explain it thoroughly. Here, this is an example of a red-black tree. It meets all the criteria of a red-black tree. Here we can see that. Here number 33 is a root node. So its color is black. Again, if you see, oh, sorry. Again, if you see the node number 13, 41, 61, 15, 13, all of these nodes are red. So its child would be black. So it's also abiding the red property. And what is the depth property? Now, in order to count the depth property, we'll not count the root node. We'll count from here. Let's say 1, 2. Let's say we'll go from 33 to this left nil node. So in order to get how many black nodes will we pass, we'll just count that. 1, the node 11, and the nil node. And again, if we go from 33 to this nil, then it's node 11 and nil. So we can see that the depth is like 2. Again, from here we can see that 33, 13, 21, 21 to nil, only just 2. So the depth is 2. Here also 2, here also 2, here also 2. Everywhere we can see that the depth is maintained. So in this way, a red-black tree works. Now, how the red-black tree maintains the property of self-balancing? The red-black color is meant for balancing the tree. The limitations put on these node colors ensure that any simple path from the root to a leaf is not more than twice as long as any other such path. It helps in maintaining the self-balancing property of the red-black tree. Operations on a red-black tree. Various operations that can be performed on a red-black tree are rotating the subtrees in a red-black tree. In rotation operation, the positions of the nodes of a subtree are interchanged. Rotation operations is used for maintaining the properties of a red-black tree when they are violated by other operations such as insertion and deletion. Now, what is rotation? There are 2 types of rotation: left rotation, right rotation. These are the fundamentals, and there are also some like edge cases. We'll discuss them later. In the left rotation, we can see that the arrangement of the nodes on the right is transformed into the arrangements of the left node. So what does this mean? Here we can see that a node named X and a node named Y. X is the child of P, let's suppose P is a parent, or else it's null, or X is the root node. So a trick is that how will you left rotate it? So in order to left rotate, we'll have to uh, we'll have to uh, we'll have to separate X and Y node. We'll have to separate X and Y node and insert the B node in the X right subtree. Now we'll we'll dismember the X node from the parent, and the parent node will go to Y. And again we'll see that A and B node will be joined to X. Now where will the X go? The X will go to the left node of Y. In this way, the uh, uh, here we can see a animation. I just found it on online, so it's a very good animation for you to visualize. You can visualize it. So it's a left rotation. Here we can see that how it's changing and how it's left rotating. I hope everyone understands. Now let's move on to the right rotation. This is also similar, but we'll just right rotate it. So which means that X will become the parent node. X will become the parent node. One more thing I want to share here is that let's suppose X is a node. Let's suppose X is a node, and Y is a nil node. Y is a nil node. Y's parent, so here Y, the parent of Y is X, and the grandparent of X is Y, and Y's uncle is A. Why we're saying that Y's uncle is A? It's important because most of the time in such cases we have to see, we have to left and right rotate according to the uncle. If the uncle is red or black, we'll see that later. Now here are some ways how to right rotate. Now this is a animation of a right rotation. Here's an animation of right rotation. So here you can clearly see that the fifth node, that is X node, will always be the parent node. I mean the grandparent node, because before the 7 was the grandparent node, now the 5 becomes the parent node of 7. So it interchanges the place. Now there are some edge cases. In left rotation, the arrangements are shifted. So what is left right and right left rotate? Here you can see in this example, you can see this is Z and this is X and Y. So if you see a type of triangle is forming like this, a type of triangle is forming, so you have to left rotate, then it will become a linear path. Now again you have to right rotate on Y, and in this way the whole tree will be balanced. This is similar to the opposite condition. First we have to right rotate, then left rotate in order to balance the tree. Now inserting an element into a red black tree. While inserting a new node, the new node is always inserted as a red node. After insertion of a new node, if the tree is violating the properties of the red black tree, then we do the following operations: recolor and rotations. So what is recolor and rotations? So here's an algorithm to insert a new node. I think no one will understand how it works. Like, I'll show you the code. Uh, why newly, we'll get into it later. We'll get into it, the algorithm later. Why newly inserted nodes are always red in a red black tree. Okay, there are some cases. So what are the cases? Here you can see that. Let's take an example. Case 1. Now if the grandparent is red, if the grandparent is red, then we will left rotate. or right rotate according to the uh, will left rotate or right no. If the grandparent, if the color of the right child of grandparent of G is red, set the color of both of the children GP as black, and the color of GP as red. Assign GP to a new node. Case 2. Now what it states that if a grandparent is red, then the uncle and the father of the node will change their color, into black, and the root node will be, and the root node, that means the grandparent would be red. Again, if the color is black, then we don't have to do recoloring. Then we'll just use the left rotate and the right rotate, and the edge cases, left right and right left rotate. So these are the three cases. Ma'am, I'll just open the IDE. Hello.
Yeah, sure.
So here I have written the Java code. Um, it's not looking pretty, I guess. Ma'am, is it okay if I explain the CPP code?
Okay.
Everything is the same, only using in Java the class, nothing else, and everything is like 95% same. 95% same. So let's start. So here you can see that we are making a structure named node, and what it will contain, a pointer of type node named parent, left and right, and it will contain two datas, that is integer and integer data and integer color. So the color is for balancing. And why are we using the parent? We are using the parent for storing the grandparent's name, vice versa. So for the ease of code, here we have written a small line, that is type def node pointer. What it does is that it replaces the node with node pointer. As a result, the code looks much cleaner. Now, let's. It's a very big code actually, 500 lines, but I don't think you'll need every one of them. So here we can see that we are calling a class, and we're also giving an object of it, red black tree. So red black tree BST. So what it does there, where is the class? So here we can see there is a class named red black tree. This is a very big class. So inside the red black tree, you can see node pointer root and node pointer tnull. So what is root and what is tnull? The root is for storing the root. I mean, the parent of the parents. You can say the parents of the parents. And what is tnull? Here tnull is the null node. And why are you using tnull? The reason we are using tnull, because that it has to be always black. So when there is also a constructor. So here is the constructor of the red black tree. Now in this constructor, what tnull does is that it assigns a new memory location with the help of new node, and will assign the tnull color, that is the leaf node color, to 0, which means black. Tnull color is black, and tnull left is equal to null pointer, tnull right is equal to null pointer. Why are you using null pointer? It's important because we have to keep there like 0. We don't have to keep any references there, and we're assigning the root to tnull. Now here is an binary search tree dot insert. So it's calling a function named insert to insert the number 55 in a node. So here is the insert function. In the insert function, we can see that we are calling a new node and we are assigning a memory location. In C, you can use malloc, but in CPP, you can just use the new keyword. So it doesn't matter. And we are assigning the parent of the null pointer to null pointer, node pointer to null pointer, and the node data to key, and the node left to tnull, and the node right to tnull, and the node color to 1. Now, every time you insert a node in a red black tree, you have to color the node to red. This is a criteria. Every time, why are we doing this? Why are we always inserting a red node? Why are we coloring red? Because the reason behind it is that if we, so it's very hard for us to solve that equation or problem, but it's very easy for us if we color it red. So we're assigning two pointer, one is y and x, and one is null pointer and another is this root. Here I have written some code. Actually, this is for testing purpose. Uh, this is for testing purpose, and this is for testing purpose only. I've written this code to see the testing purpose. So this part of the code, what it does is that uh, it points to a null pointer. One of the pointer points to a null pointer, and another pointer points to the root. Now, while x is not equal to tnull, what we do here is that here we are actually assigning the node. In binary search tree, I'm not saying red black tree, in binary search tree, in order to assign a node, we have to go at the root of it. So similar type of thing we are also doing here. So what are we doing here? We are going to the root of it. How are we going to the root of it? Because we know the root would be tnull. The root would be tnull. We'll go until it is tnull. So since y is null pointer, we'll assign y with x. If node of data is smaller than x data, then x is equal to x left, else x is equal to x right. Now we have gone to the edge of the tree. Now we will mark the parent of node of parent. Node of parent is equal to y. Now we'll mark the node of parent y. Now, if the parent of y is null pointer, then we'll say that the root would be the node, which means that we have just inserted a first value. Nothing is inserted before. Now, if node of data is smaller than y of data, then y of left is equal to node, and else y of right is equal to node. This piece of code we're using it for assigning it to a left or right subtree. If node of parent is equal to null pointer, then node of color is equal to 0. What is null pointer? If node of parent is equal to null pointer, node of color is equal to 0. There is a condition that if the node is root, then the color of the root would be black. This is a prerequisite. And if the parent of that means the grandparent is null pointer, then we would just return. Now we have done something. We have inserted you could say we have inserted a node in a tree. Now since we have inserted a node in a tree, now we have to fix the many violations that has happened. We have to fix the many violations that has happened. So what are the violations? So let's see. Fix the violation of node X, the node we have inserted. So here we can see that for balancing the tree after insertion. So this is the node pointer K, and what we have to do with K is that we have to fix the violation of K if it violates any of the 5 problems. characteristics. Now in node pointer u, uh, a hint is that this node pointer is an uncle, uncle. This node pointer is an uncle, so it would be easy for you to visualize. Now if case parent color is 1, if case parent color is 1, if case parent color is 1, then what we'll do? Now what is this? You could say if case parent color is 1. Now in here, let's take now just for an example, let's take this one. Here, let's say this is y is k and x is its parent. So if the parent of y, that is x, is red, if it's red, then we will insert the loop. Now we'll see if case parent is equal to case parent parent right. If case parent is equal to case parent parent right, what does this mean? That uh, if its parent right, if I belong to the right subtree of my parent, if I belong to the right subtree of my parent, then what we will do? We'll assign the uncle u of case parent parent left, and we'll color it red. Here we'll color it, red, and the here we'll color it red, and we'll color uncle to black, and the parent to also black, the parent also black, and we'll color the root node, that is grandparent, that is grandparent, to red. So this piece of code, what it does is that it just changes the color. Here we are not using any left or right shift, but if the uncle is black, now we can do left or right, right rotate or left rotate. This else case is for if the uncle is black. If the uncle is black, then what we will see here is an if case to right rotate and then left rotate. So why are we using right rotate and left rotate at the same time, you may ask? So the reason is that since I have shown you some edge cases, if it forms like this, a triangle, then what we will do? First we will do left rotate and then we will do a right rotate. But if it forms like this, the second case, then we'll just right rotate it. There's no need to left rotate. So we're doing this trick here. Again, the vice versa of this code is this part. This is the vice versa, the opposite part. Now, if case root is if k is equal to root, then we'll just break. We'll just break the red black tree, while loop of red black tree. Why will break the while loop of red black tree? Because after solving each of them recursively, and validating the answer, we'll just break the loop when we will reach the root node, and we'll color the root to 0, because the color of the root doesn't matter actually, but we are coloring it 0, which is black. Now, two things to take into consideration: how the right rotate works and how the left rotate works. Now here's a code of how the left rotate works and how the right rotate works. So this is a code of left rotate. The same thing, the opposite thing applies for the right rotate. If you have understood the animation, then it would be very easy for you to know how the right rotate works. And here are the pictures. How does it work? Assign the parent of y as the parent of x, then assign x as the parent of y. In this way, you'll get right rotate. See, we are assigning x right to y left, and while y left is not equal to t null, so we'll get to the root of it, and we'll assign it something x, then y's parent is equal to x parent, and we'll get the root if it's null pointer, else if x parent is left and x parent of left is equal to y. In this way, we'll just left rotate it. This is right rotate. In this way, you can insert something in the table, and the other codes are for pre-order, in-order, and post-order traversal in a red black tree. This is also search, minimum, maximum, and nothing more. Now let's go to the algorithm. Now, following steps are for inserting a new element in a red black tree. Let y be the leaf that is nil and x be the root of the tree. Check if the tree is empty, whether x is null. If it's null, then insert a new node as a root node and color it black. Else, repeat following steps until leaf nil is reached. Compare new key with root key. If new key is greater than root key, traverse through the right subtree, else traverse through the left subtree. Assign the parent of the leaf as a parent of new node. If leaf key is greater than new key, make new node as right child, else make new node as left child. Assign null to the left and right child of a new node, assign red to the new node. Call insert fix algorithm to maintain the property of a red black tree if violated. It's a pretty hard topic to grasp, so I would suggest you to hear the references. So red black tree, I have found that programmist.com, they have written a very thorough discussion about how does this tree works, and I forgot to include the YouTube references, but let me see. The YouTube references would be Michael. There is a YouTuber named Michael Sambol. Michael Sambol, you can watch his playlist. So he explains red black tree very thoroughly, and there's also a YouTuber named Mr. Code. So I'll just write it down. Michael Sambol. Michael Sambol, and another YouTuber named Mr. Code. Mr. Code. Both of them have a playlist of red black tree, so you can watch these playlists. And thank you everyone, and special thanks to Linta ma'am for giving me this opportunity.